Picture humanity as contestants on the universe's strangest game show, and 3 Atlas just revealed our prize options. Behind door number 1, revolutionary science that transforms our understanding of planetary formation. Behind door number 2, a quiet passage that changes nothing except a few textbook footnotes. Behind door number 3, well, that's where things get interesting. Like cosmic Russian roulette played with interstellar objects. Every new visitor presents a ranked menu of possibilities. Some delicious, some dangerous, and most surprisingly mundane. But in the case of 3 Atlas, mundane is the last thing that comes to mind. We've catalogued every potential outcome from transformative discovery to tabloid nightmare. Stay with us to learn which prize humanity is most likely to win, and which scenarios await us in the coming months. What 3 Atlas is and why it matters. In the summer of 2025, something changed forever. Not with fanfare or with warning, but with the quiet, almost imperceptible click of a camera shutter. It happened in the high, dry air of the Chilean mountains. What the Atlas survey saw that July 1st night was nothing short of extraordinary. But it was also a whisper, a faint smudge of light against a backdrop of billions of stars. It was a visitor that had traveled for millions, perhaps even billions of years, all just to pass through our celestial neighborhood. Meet 3 Atlas, the 3rd confirmed interstellar object ever discovered. While you were sleeping, while you were working, while humanity carried on with its daily routines, this ancient silent wanderer was already racing toward our Sunday. It was moving at 57 kilometers per second. That is fast enough to circle the entire Earth in just 12 minutes. It is fast enough to leave our solar system behind forever. But speed alone does not make something interstellar. What marks 3 Atlas as truly fundamentally alien to our system is its orbit. It follows a hyperbolic trajectory with an eccentricity of approximately 6. In the precise, unforgiving language of celestial mechanics, this means one thing and one thing only: it will never return. Unlike the comets that we are familiar with, the ones that swing around our sun in predictable repeating ellipses, they are like cosmic boomerangs. 3 Atlas follows a path that bends but never closes. It came from somewhere else entirely, and it is going somewhere else entirely. The discovery of this object unfolded with a methodical, almost beautiful precision that defines modern astronomy. The first detection was on July 1, 2025. It was captured by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. But astronomers are careful, patient people. They dug deeper, scrolling through the vast digital archives of images. They were searching for earlier unnoticed glimpses of this traveler, and they found them. Pre-discovery observations stretched all the way back to June 14, 2025. They revealed this visitor had been silently announcing its presence for weeks, long before anyone had noticed. The official designation followed quickly: 3I, which means the 3rd interstellar object, and Atlas honoring the survey that first found it. Behind this seemingly bureaucratic and mundane naming convention lies something profound. We now live in an era where visitors from other star systems are common enough to require a filing system. Where is it going? The mathematics are unforgiving and precise. Perihelion, its closest approach to our Sun, will occur around October 29th to 30th, 2025. It will be at approximately 1.36 to 1.4 astronomical units. That is roughly 204 million kilometers from the Sunday. This places it somewhere between the orbits of Earth and Mars at its nearest point. For those keeping track of existential threats, 3 Atlas will pass closest to the Earth in mid-December of 2025. It will be at about 1.6 to 1.8 astronomical units. That is roughly 270 million kilometers away. To put that vast distance in a human perspective, it is further than the gap between Earth and Mars at their closest approach. There is zero impact risk, none. The mathematics of orbital mechanics do not deal in maybes, not when it comes to trajectories that are this well defined. But what exactly are we looking at? The early observations with the Hubble Space Telescope on July 21st revealed something that was both familiar and profoundly alien. A teardrop-shaped dust coma, the hallmark signature of a comet that is awakening under the powerful influence of the Sunday. These first fleeting glimpses suggest a nucleus no larger than 5.6 kilometers across, though it could be significantly smaller. We are not talking about a mountain-sized chunk of ice and rock. It is more like a large hill with delusions of grandeur. Yet the size, as we will soon discover, may be completely irrelevant, not compared to what this ancient object carries within its frozen structure. Here is what we know with complete confidence. 3 Atlas is definitely interstellar, it is definitely active, and it is definitely safe. Its orbit class is confirmed. Its rough activity level is measurable, and its distance from the Earth is comfortably vast. But here is what we do not know: the exact size of its nucleus, its precise shape, its detailed chemical composition, or most intriguingly, the specific stellar nursery where it was born. This uncertainty is not a failure of science. It is the very edge of discovery, the place where known facts meet infinite possibility. Why does any of this matter? Because 3 Atlas carries a chemical fingerprint from another solar system, a fingerprint held within its frozen, pristine structure. While Earth's comets were formed in our own sun's disk 4.6 billion years ago, this visitor was formed around a completely different star. It was formed under completely different conditions, with completely different materials available. It is a geological sample from a world that we will never visit, and it's delivered directly to our most sophisticated instruments. Every molecule of water ice, every single grain of dust, and every trace of carbon monoxide represents a data point. A data point in the grand cosmic experiment of planetary formation. How do other star systems build their worlds? What materials were common in the ancient galaxy? How similar or how different are the processes that created our own Earth's neighborhood? 3 Atlas offers the answers, but only if we are smart enough to ask the right questions and sophisticated enough to interpret what we find. The name itself tells a story. Atlas, the Asteroid Terrestrial Impact Last Alert System, was designed to spot potentially hazardous objects, the kind that might one day threaten the Earth. Instead, it found something that poses no threat at all, but it offers something far more valuable: a perspective. We are not alone in this galaxy, not in the sense of little green men, but in the sense that planetary systems form, evolve, and occasionally share their leftovers across interstellar space. As we embark on this investigation, we will separate what we know from what we hope, what has been peer-reviewed from what is still being debated, and what is scientifically sound from what is pure, unadulterated speculation. The truth about 3 Atlas is remarkable enough without any embellishment. We stand at the very threshold of discovery, watching an ancient traveler make its brief, fleeting appearance in our cosmic backyard. What it teaches us may reshape our understanding not just of comets, but of how planetary systems across the entire galaxy build themselves from dust and a dream. The question is not whether 3 Atlas will change everything. It is how much and in what ways we are prepared to let it. The S-tier outcome, the scientific windfall. What if everything we thought we knew about comets was wrong? What if the neat, tidy categories we have built were just a limited perspective? The water-rich, the carbon monoxide enhanced, the typical this, the normal that. The perspective of creatures who had only ever seen comets from one single star system. 3 Atlas is rewriting the textbooks in real time. The first bombshell came from the James Webb Space Telescope, humanity's most sophisticated eye in space. The JWST's near-infrared spectrograph detected something that made astronomers double-check their instruments: unusually strong carbon dioxide emissions when compared to water. The early estimates suggest a ratio approaching 8 to 1. 8 parts of carbon dioxide for every 1 part of water vapor. For context, typical solar system comets show the exact opposite pattern, a pattern where water dominates the chemical mixture. This is not just unusual, this is extraordinary. But the JWST was not alone in its surprise. The SPHEREX mission, designed to map the entire sky in infrared light, turned its attention to 3 Atlas, and it discovered something even more puzzling. The carbon dioxide coma, the vast cloud of gas and dust surrounding the nucleus, extends for at least 348,000 kilometers. That is nearly the distance from the Earth to the Moon. Meanwhile, water and carbon monoxide, the very substances that typically announce a comet's presence, they were not detected in those observations. Now, before we get carried away, let's acknowledge what we are dealing with. These are preliminary results, the kind that make scientists both excited and incredibly nervous. The teams analyzing this data are still refining their measurements. They are still double-checking their calibrations. What we are witnessing is science in action, the messy, iterative process of turning raw data into an understanding. But even with appropriate caution, the implications are staggering. The carbon dioxide dominance suggests 2 primary scenarios. Each one has profound consequences for our understanding of planetary formation. The first possibility is that 3 Atlas was formed beyond the carbon dioxide ice line in its home star system, in the frigid outer reaches where carbon dioxide freezes before water does. This would place its birth in the equivalent of our own outer asteroid belt or beyond, in the cold, dark regions where only the most volatile substances remain gaseous. The second possibility is that the nucleus has developed a surface crust, a crust that effectively suppresses water sublimation while allowing carbon dioxide to escape. Think of it as a cosmic thermos bottle, an outer layer that insulates the interior and controls which materials can outgas under solar heating. Both of these scenarios require us to fundamentally reconsider our models of how outer protoplanetary disks distribute their chemical ingredients. We are not just looking at one weird comet, we are potentially glimpsing an entirely different approach to building worlds. The coordination of observations across multiple facilities represents a masterclass in modern astronomy. The JWST provides detailed molecular fingerprints through its near-infrared spectrograph. The Hubble captures morphology and size constraints with its incredible resolution. SPHEREX contributes wide-field spectral mapping that captures the extended environment around the nucleus. And ground-based telescopes at the Gemini Observatory and NOILAB add complementary imaging and spectroscopy from Earth's surface. Each instrument sees something different, but together they are assembling a portrait of an object unlike anything in our own solar system's family album. The comparative context makes 3 Atlas even more intriguing. 2 Borisov, our previous interstellar comet visitor, behaved like a perfectly normal comet. Water-dominated, predictable, and familiar. It fit comfortably into our existing understanding of how comets work. 1 Oumuamua, our first confirmed interstellar visitor, was so unusual that astronomers are still debating on whether it was a comet at all. Some evidence suggested it might have been more of an asteroid than a comet or something else entirely. 3 Atlas fills a crucial gap in this small but growing catalogue. It is definitely a comet. The dust coma and the outgassing leave no doubt. But it is a comet that challenges our assumptions about what normal means in the broader galaxy. The payoff extends far beyond comet science. Volatile ratios like the ones 3 Atlas is revealing help astronomers locate birth zones. They help reconstruct the thermal histories in protoplanetary disks across the entire galaxy. Every star system builds itself differently, using whatever raw materials are available and following the specific dynamics of mass, temperature, and time. By studying the chemical signatures of interstellar visitors, we are essentially conducting archaeology on a planetary formation process that occurred billions of years ago, around stars that we will never visit. The data legacy aspect deserves special attention. Unlike fleeting phenomena that disappear forever, astronomical data sets tend to improve with age. The raw images and spectra being collected now will be reanalyzed for decades to come. As calibration techniques improve and new analysis methods are developed, NASA and the ESA maintain open archives specifically for this purpose. This ensures that today's observations become tomorrow's breakthrough discoveries. This global campaign represents coordination at its finest. The observing windows have been carefully orchestrated to maximize science return. Even though Earth will be poorly positioned during perihelion, when 3 Atlas swings closest to the Sunday spacecraft scattered throughout the solar system will pick up the observations. They will do so when ground-based telescopes lose their view. This creates a continuous record of the comet's evolution. The theoretical implications ripple outward like the waves from a dropped stone. If 3 Atlas truly originated in the galactic thick disk, a population of older metal-poor stars formed during the galaxy's youth, then we are examining material that predates Earth's formation by billions of years. We are literally holding a piece of cosmic history in our scientific instruments, a sample from an era when the universe was fundamentally different. But let's be honest about the controversy. Active debate continues about whether 3 Atlas comes from the thick disk or the thin disk, whether its parent system was ancient or relatively recent, and whether its unusual chemistry represents primordial conditions or a later evolution. Science thrives on such disagreements, using them as fuel for better observations and more sophisticated analysis. The jackpot here is not a spectacle, it is precision. While the general public might hope for dramatic photos or visible tail displays, the real treasure lies in the sharp chemical signatures and precise dynamical measurements. Measurements that constrain the models of how planetary systems form across the entire galaxy. Every spectral line, every velocity measurement, and every photometric data point represents a piece of evidence. Evidence in the grand jury trial of planetary formation theory. 3 Atlas is teaching us that our solar system, for all its familiarity, represents just one approach. One approach to building worlds from cosmic dust. Other stars, other systems, and other approaches exist. And occasionally, if we are very lucky and very prepared, those other approaches come to visit. The question is no longer whether interstellar objects will revolutionize our understanding of planetary formation. The question is how quickly we can learn to read the messages that they carry. The A-tier outcome, mission alignment, and tech spillovers. Sometimes the most profound discoveries happen not because we build something new, but because we are clever enough to point existing tools in the right direction, to do so at precisely the right moment. The beauty of 3 Atlas lies not in requiring some massive new space mission, though that would be exciting, but in how it perfectly aligns with humanity's existing scientific infrastructure. We do not need to spend billions of dollars or wait decades for launch windows. We just need to be smart about coordination and opportunistic about timing. The reality of modern astronomy is that the most capable instruments are already in space. They are already operational and already delivering groundbreaking science on a regular schedule. The JWST is revolutionizing infrared astronomy. The Hubble continues its legendary service despite decades in orbit. The SphereX is mapping the entire sky. The challenge is not building new capabilities, it is orchestrating the ones we have. And the orchestration for 3 Atlas is remarkable. The JWST can pivot small fractions of its observing time toward the comet during key windows, using its unparalleled infrared sensitivity to dissect molecular emissions with unprecedented precision. The Hubble adds its legendary resolution for morphology study and size constraint. SphereX contributes wide-field spectral mapping that captures the extended environment around the nucleus. On the ground, the coordination extends across continents. Gemini North and South provide complementary observations from both hemispheres. The Palomar Observatory adds its own perspective, and Oumuamua coordinates across multiple facilities to ensure comprehensive coverage. But here is where it gets interesting. Some of the best observations might not come from Earth at all. Spacecraft scattered throughout the solar system find themselves in uniquely advantageous positions during the passage of 3 Atlas. The JUICE mission, fresh from its August 31st Venus gravity assist, will be approximately 68 million kilometers from the comet during key observation windows. NASA's Psyche spacecraft, en route to its metallic asteroid target, sits roughly 45 million kilometers away. The Mars orbiters enjoy front-row seats at distances of just 29 million kilometers. These include NASA's Mars Reconnaissance Orbiter, Chinese Tianwen-1, and the UAE's HOPE mission. These are not purpose-built comet missions. They are existing spacecraft with their own primary objectives, with their own carefully planned timelines and scientific priorities. But geometry and timing have aligned to offer unprecedented opportunities for multi-platform observations of an interstellar visitor. The advantages of spacecraft observation become crucial around perihelion. This is when Earth's view of 3 Atlas becomes severely compromised by solar glare. While ground-based telescopes lose sight of the comet behind the sun's overwhelming brightness, spacecraft positioned throughout the solar system maintain clear lines of sight. They can watch the comet's tail develop, they can monitor its outgassing behavior, and they could potentially even sample dust particles if orbital mechanics aligns favorably. These observations are not guaranteed, they are opportunistic. Spacecraft instruments are not necessarily optimized for comet science, and primary mission requirements take priority. But even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data about how 3 Atlas behaves when it is impossible to observe from Earth. The public engagement potential deserves recognition. Live-streamed observing sessions have proven to be enormously popular for previous interstellar visitors, particularly from major ground-based facilities like Gemini South. Citizen science projects that allow the public to participate in data analysis add another layer of engagement. When the general public can directly contribute to cutting-edge science, it transforms abstract research into a personal investment. Behind the scenes, 3 Atlas is driving technological improvements that will benefit all of future astronomy. Moving targets require more sophisticated tracking algorithms, faint objects demand better noise reduction techniques, and cross-facility coordination needs robust data-sharing protocols. Each of these challenges pushes the boundaries of what is technically possible, creating solutions that benefit far more than just comet science. The data tooling upgrades are particularly significant. Better pipelines for processing observations of moving targets will improve many things: asteroid surveys, planetary mission operations, and space situational awareness. Enhanced cross-calibration between the JWST SphereX and Hubble creates more reliable photometric standards for all astronomical observations. These are not just improvements for this one comet, they are infrastructure upgrades for the entire field. Future mission concepts are already incorporating the lessons learned from the 3 Atlas observations. The Comet Interceptor mission represents a new philosophy. Instead of launching toward a specific target, a spacecraft is positioned at a gravitationally stable point. There it waits for interesting objects to announce themselves. 3 Atlas validates this approach. It demonstrates both the scientific value of interstellar visitors and the practical challenges of late discovery and high velocity. The budget reality check is crucial here. This entire scientific windfall does not require congressional appropriations or multi-year development programs. It is primarily a matter of coordination, scheduling, and data sharing among existing facilities. The most expensive component might be the extra staff time needed to analyze the resulting datasets. That is not to minimize the complexity. Coordinating observations across multiple space agencies, ground facilities, and spacecraft missions requires finesse. It requires diplomatic finesse and technical precision. Time on premier facilities like the JWST and Hubble is extraordinarily valuable. It is allocated through competitive processes months or years in advance. Pivoting even a small amount of observing time toward 3 Atlas represents a significant commitment, but the return on investment is extraordinary. For a relatively modest coordination cost, humanity gains its most comprehensive look yet at material from another star system. We develop new techniques for rapid response observation of transient targets. We demonstrate international cooperation in real-time science, and we inspire the next generation of scientists and engineers. The lesson extends beyond this single comet. In an era of increasingly expensive flagship missions and decade-long development cycles, 3 Atlas demonstrates the continuing power of smart coordination among existing assets. Sometimes the most profound discoveries do not require the newest, biggest, and most expensive tools. They require the wisdom to use what we have most effectively. As we watch this coordination unfold, we are witnessing a preview of how science will work in the era of routine interstellar visitors. The infrastructure is largely in place, the techniques are being refined, and the international cooperation frameworks are being tested. 3 Atlas is not just a comet, it is a proof of concept for 21st century astronomy. The C-tier outcome, the quiet pass. Not every cosmic visitor arrives with fanfare. Not every scientific breakthrough comes wrapped in spectacle and a social media buzz. Sometimes the most profound discoveries happen quietly, methodically, without changing anyone's weekend plans or inspiring Hollywood blockbusters. This is the most likely scenario for 3 Atlas, and that is perfectly fine. The geometry of the situation works against dramatic visibility. When 3 Atlas reaches perihelion in late October of 2025, the Earth will be poorly positioned for observations. The comet will be lost in solar glare, invisible to casual observers, and accessible only to specialized spacecraft and carefully planned professional observations. There will be no naked eye spectacle, no social media photos of a brilliant tail stretching across the sky, and no reason for people to gather in parks with binoculars. Instead, there will be data sets, lots of them. The observational cadence tells the story, intense monitoring as the comet approaches. A solar conjunction gap when Earth-based observations become impossible, and then resumed observation in December as 3 Atlas emerges from behind the sun's glare. This structure shapes what we learn, and when we learn it, it creates a natural progression from approach characterization to post-perihelion analysis. During the solar gap, spacecraft positioned throughout the solar system continue their work. The Mars orbiters monitor the comet's behavior when it is closest to the Sun. The deep space missions track its tail development. The solar observatories capture its interaction with the solar wind. The data collection never stops, it just shifts platforms. For most people, this will feel like a non-event. News coverage will be respectful but restrained. Scientists study a distant comet rather than death from space narrowly avoids Earth. Educational institutions will incorporate 3 Atlas into lesson plans, lessons about the solar system and the scientific method. Space agencies will publish regular updates with measured language about scientific progress and international cooperation. This measured response represents healthy scientific communication. 3 Atlas is fascinating to scientists and genuinely important for our understanding of planetary formation. But it is not going to fundamentally alter daily life for anyone outside the astronomical community. The story is a safe, distant, beautiful data set, not a once-in-a-lifetime sky event. The quiet nature of this outcome creates a space for genuine scientific education. Without sensationalism or a crisis framing, there is room to explain how uncertainty works in science, how preprints differ from peer-reviewed papers, and why patience is essential to discovery. These are crucial lessons for scientific literacy, but they are often overwhelmed by more dramatic narratives. Consider the educational value of watching science work normally. The public can follow along as initial observations get refined, as preliminary results undergo peer review, and as competing hypotheses get tested against new data. This is how science actually functions, not through sudden revelations or paradigm-shifting announcements, but through a careful accumulation of evidence and a gradual refinement of understanding. The professional community benefits enormously from this approach. Cross-validation between different instruments and facilities proceeds without external pressure. Negative results and non-detections get appropriate attention rather than being dismissed as boring. Long-term studies can develop without the distraction of constant public explanation and media management. From a policy perspective, the quiet outcome supports steady, sustainable funding for astronomical surveys, not the boom and bust cycles driven by public excitement. Programs like Atlas Linear and the upcoming Rubin Observatory need consistent support over decades to function effectively. Sensational events can trigger short-term funding increases, but they can also create unrealistic expectations about the pace and nature of discovery. The cultural impact, though subtle, may be more profound than an immediate spectacle. 3 Atlas normalizes the idea that our solar system is not isolated, that material moves between star systems, and that we live in a galactic neighborhood where visitors occasionally stop by. This represents a fundamental shift in how humanity thinks about its cosmic context, but it is the kind of shift that happens gradually through accumulated awareness, not a sudden revelation. For astronomers, the quiet outcome allows a focus on what matters most: the data. Without media circuses or public pressure for immediate results, research teams can take the time needed for proper calibration, thorough analysis, and careful interpretation. The resulting papers will be more reliable, more comprehensive, and more useful for future research. The long-term scientific value often exceeds the immediate impact. The datasets from 3 Atlas will be archived and reanalyzed for years to come, as techniques improve and new questions arise. Today's preliminary results become tomorrow's refined measurements, which become next year's theoretical insights, which become the next decade's textbook examples. This pattern repeats throughout astronomy. Many of the most important discoveries in the field were initially unremarkable, just catalogued objects that became crucial years later when better analysis techniques revealed their significance. Pulsar timing arrays, gravitational wave detection, and exoplanet discovery all followed this pattern. A pattern of quiet accumulation leading to a revolutionary understanding. The international cooperation aspect continues regardless of public attention level. Scientists from different countries and institutions collaborate on data analysis, on instrument calibration and theoretical interpretation. These professional relationships strengthen the global scientific community, and they establish frameworks for future discoveries. The data-sharing protocols developed for 3 Atlas will benefit other moving target observations. The rapid response coordination techniques will improve responses to future interstellar visitors. The cross-facility calibration methods will enhance all astronomical observations involving multiple telescopes. Even in the quiet scenario, citizen science opportunities remain available. Image processing projects, data validation tasks, and educational programs can engage the interested members of the public, all without requiring mass participation or media attention. Quality over quantity often produces better results in citizen science contexts. The absence of drama does not mean an absence of discovery. Some of the most significant advances in our understanding of planetary formation have come from careful analysis. From the analysis of unremarkable objects, 3 Atlas could easily fall into this category, scientifically crucial, but publicly invisible. Perhaps most importantly, the quiet outcome allows 3 Atlas to establish baselines for future interstellar visitor studies. The observational techniques, analysis methods, and coordination protocols developed for this object will inform future responses. Responses when a discovery's timing, geometry, or characteristics might be more favorable for public engagement. The expectation versus reality gap matters here. Managing public expectation appropriately, emphasizing scientific value over visual spectacle, creates healthier relationships between professional astronomy and public understanding. Science communication works best when it is honest about what to expect and why it matters. In the end, the quiet pass scenario represents science at its best. Careful, methodical, international, patient, and focused on understanding rather than entertainment. Not every cosmic event needs to be a blockbuster. Sometimes the most valuable discoveries happen when scientists can work without distraction. Building knowledge step by careful step. The universe is full of quiet wonders. 3 Atlas may be one of them. The F-tier myths, the cinematic worst cases, and why they are not on the table. Let's get the nightmares out of the way first, because in our age of social media panic and cinematic disaster fantasy, someone is going to ask, can 3 Atlas destroy the Earth? Can it trigger solar flares? Can it somehow hide behind the sun and launch a surprise attack? The short answer is no. The long answer involves some very satisfying mathematics. Mathematics that demonstrate exactly why these fears are not just unlikely, but physically impossible. Start with the impact scenario, because that is usually everyone's first concern. 3 Atlas will approach no closer than approximately 1.6 astronomical units from Earth. That is roughly 270 million kilometers. To put this in perspective, this is farther than the distance between Earth and Mars at their closest approach. It is like worrying about a car accident when the other vehicle is in a different time zone. But let's be more precise about this. The gravitational influence of any object falls off as the inverse square of a distance. At 270 million kilometers, 3 Atlas would exert less gravitational pull on the Earth than a large building exerts on you when you walk past it. Even if it was somehow much larger and more massive than current observations suggest. The gravitational chaos myth deserves special attention because it sounds almost scientific. Could 3 Atlas somehow disrupt planetary orbits or destabilize the solar system? The mathematics are brutal in their clarity. Even if 3 Atlas were 1,000 times more massive than current estimates suggest, its gravitational effect on planetary motion would be utterly negligible. Consider the mass ratios involved. The Earth weighs approximately 6 times 10 to the 24th power kilograms. Jupiter weighs about 318 times more than Earth. The Sun weighs about 330,000 times more than Earth. 3 Atlas, generously assuming a 5-kilometer radius and typical comet density, weighs perhaps 10 to the 14th power kilograms. That means Earth outweighs 3 Atlas by roughly 60 billion to 1. The idea that this tiny iceberg could meaningfully perturb a planet is like suggesting something absurd. Suggesting that a mosquito could deflect a freight train by flying into it. The doomsday tail scenario requires its own mathematical reality check. Comet tails consist of incredibly tenuous gas and dust, far less dense than the best vacuum we can create in terrestrial laboratories. At astronomical distances, even passing directly through a comet tail poses no meaningful threat to a spacecraft, let alone the planets. The material is so diffuse that you could compress an entire comet tail into a sphere, and it might weigh less than a car. Moreover, 3 Atlas will not come anywhere near the Earth. Its tail, no matter how spectacular it might appear, consists of particles following slightly different trajectories than the nucleus. These particles will disperse across millions of kilometers of space, creating a beautiful but utterly harmless display for any spacecraft positioned to observe it. Now, for the truly creative conspiracy, it is hiding behind the sun to attack. This myth demonstrates a fundamental misunderstanding of both orbital mechanics and the nature of observations. 3 Atlas is not hiding. It is following a predictable trajectory, calculated from hundreds of observations by dozens of facilities worldwide. The solar conjunction period, when Earth-based observations become difficult, is a consequence of geometry, not strategy. During this period, spacecraft positioned throughout the solar system will maintain clear lines of sight to the comet. The Mars orbiter's deep space missions and solar observatories will continue monitoring its behavior. There is no concealment, no surprise capability, and no strategic positioning. There is just a comet following Newton's laws of motion with clockwork precision. The size mythology needs addressing too. Early media reports occasionally conflate brightness with size. This suggests that 3 Atlas might be much larger than current estimates indicate. But brightness depends on surface area reflectivity and outgassing activity, not just size. A small, highly active comet can appear brighter than a large dormant one. Current observations constrain the nucleus to no more than about 5.6 kilometers across, and possibly much smaller. Even if 3 Atlas were larger than estimated size alone does not create danger at these distances. A 10-kilometer comet at 270 million kilometers is still utterly harmless to Earth. It's like worrying about getting wet from a water balloon thrown from the next state over. Let's establish an evidence standard for the rest of our investigation. Peer-reviewed papers carry the most weight, followed by preprints undergoing review, followed by conference presentations and press releases. An extraordinary claim requires extraordinary evidence, and the more extraordinary the claim, the higher the evidence bar should be. NASA's official communications about 3 Atlas consistently emphasize its safe distance and predictable behavior. These are not bureaucratic cover-ups or attempts to prevent panic. They are accurate summaries of what the orbital mechanics actually show. When space agencies around the world agree on basic facts like trajectory and closest approach distance, those facts are extraordinarily reliable. The scientific community has developed sophisticated methods for detecting and characterizing potentially hazardous objects. The same surveys that found 3 Atlas routinely identify and track asteroids and comets, objects that could pose genuine risks to Earth over time scales of centuries. These systems work, they are constantly improving, and they are operated by people whose careers depend on accuracy. Media literacy becomes crucial here. Headlines designed for clicks do not always reflect the content of the articles they introduce, and the articles do not always accurately represent the scientific papers they discuss. The most reliable information comes directly from the space agencies, from major observatories and the scientists actually conducting the observations. Visual effects in movies and television create unrealistic expectations about how space objects behave. Real comet tails are usually invisible to the naked eye. They extend in directions determined by solar wind rather than orbital motion, and they consist of material so tenuous that it barely qualifies as matter at all. Real asteroid impacts require very specific size and velocity combinations to cause significant damage. Real orbital mechanics follow predictable mathematical rules, rules that do not allow for dramatic last-minute course changes or surprise attacks. This myth-busting is not meant to dismiss curiosity or discourage questions. Healthy skepticism and scientific inquiry go hand in hand, but they work best when directed toward understanding what is actually happening, not imagining what might be happening if the laws of physics worked differently. Here is our promise for the rest of this investigation. We will clearly distinguish between peer-reviewed results, preliminary findings, and speculative possibilities. We will show our work when we make claims about distances, masses, and energies. We will acknowledge uncertainty when it exists, and avoid certainty when it does not. Free Atlas offers plenty of genuine mysteries that are worth exploring. We do not need to invent fictional dangers to make it interesting. The truth about this interstellar visitor is remarkable enough without embellishment, and it is threatening enough to our preconceptions without being threatening to our planet. Gravity tides and orbital mechanics keep it real. Mathematics does not lie. It does not exaggerate for dramatic effect. It does not hedge its bets for political reasons, and it does not care about our hopes or our fears. When we apply the cold, precise language of orbital mechanics to 3 Atlas, the story it tells is both reassuring and illuminating. Let's start with the fundamentals of what makes an orbit hyperbolic. Every orbit has an eccentricity, a number that describes how stretched or circular the path is. Circles have an eccentricity of 0. Ellipses have eccentricities between 0 and 1. Parabolas have an eccentricity of exactly 1. And hyperbolas, the mathematical curves describing escape trajectories, have eccentricities greater than 1. 3 Atlas has an eccentricity of approximately 6. This is not a measurement uncertainty or a preliminary estimate subject to revision. This is a fundamental characteristic. It was determined by hundreds of precise position measurements from multiple observatories worldwide. An eccentricity of 6 means the object is moving far too fast to be captured by the Sun's gravity. It came from interstellar space. It will return to interstellar space. And there is nothing in our solar system massive enough to change that fact. The velocity at infinity is approximately 57 to 58 kilometers per second. This is the speed 3 Atlas would maintain if traveling through empty space, far from any gravitational influence. This is its cosmic baseline speed, a velocity it carries as a relic of its formation and ejection from another star system. When combined with the Sun's gravitational influence, this velocity determines every aspect of the trajectory. The trajectory of 3 Atlas through our solar system. That inbound trajectory traces back to the constellation of Sagittarius, not because 3 Atlas originated there recently, but because that is the direction it was traveling when it entered the sphere of the Sun's gravitational influence. The actual journey from its birth star to our solar system likely took millions of years, and it involved a much more complex path through the galaxy's gravitational landscape. Here is where the mathematics becomes simultaneously elegant and reassuring. Once 3 Atlas entered our solar system, its entire future path became precisely predictable. Newton's laws of motion and gravity do not allow for surprises, course corrections, or dramatic last-minute changes. Every spacecraft navigation team in the world can calculate this trajectory to extraordinary precision. They use equations that have not changed since the 17th century. The perihelion distance of 1.36 to 1.4 astronomical units places 3 Atlas well outside Earth's orbit, even at its closest approach to the Sunday. That is roughly 204 million kilometers, or about 1.5 times the distance from the Earth to the Sunday. Even if 3 Atlas were somehow equipped with rocket engines and guidance systems, which it is not, the energy required to alter its course enough to threaten Earth would be beyond anything humanity has ever built. A planetary deflection during the passage is real, but minuscule. As 3 Atlas swings past the Sun, it will experience gravitational influences from Jupiter, Saturn, and other planets. These influences will slightly modify its outbound trajectory, changing its direction by fractions of degrees and its speed by meters per second. But the fundamental character of the orbit remains unchanged, hyperbolic in and hyperbolic out. The closest approach to Earth occurs in mid-December of 2025. At approximately 1.6 to 1.8 astronomical units, roughly 270 million kilometers. At this distance, 3 Atlas exerts less gravitational force on the Earth than the Earth exerts on the International Space Station. The tidal effects are so negligible that they fall below the threshold of measurement by our most sensitive instruments. To understand why, consider the mathematics of tidal forces. These forces depend not just on mass and distance, but on the gradient of a gravitational field strength. The Moon creates noticeable tides on Earth because it is relatively close and relatively massive. 3 Atlas, even at its closest approach, is nearly 700 times farther away than the Moon, and it's perhaps 1 trillion times less massive. Even if we wildly overestimate the mass of 3 Atlas, imagining it is somehow 10 times larger and denser, the tidal effects on Earth would still be immeasurably small. You would have more tidal influence on the Earth by jumping up and down in your backyard, more than 3 Atlas has at its closest approach. The orbital inclination adds another layer of safety and predictability. 3 Atlas approaches the solar system at a high angle relative to the plane where the Earth and other planets orbit. This retrograde high inclination trajectory is actually typical for random interstellar objects. It is exactly what you would expect from something that originated in a completely different stellar environment, with no relationship to our solar system's formation. Could the Sun somehow capture it? This question reveals a fundamental misunderstanding of orbital energy. A capture requires removing exactly the right amount of kinetic energy at exactly the right moment. A natural capture is extraordinarily rare. It requires very specific circumstances, usually involving a multi-body gravitational interaction or atmospheric drag, neither of which applies to 3 Atlas. The escape energy dominates everything else. 3 Atlas carries enough kinetic energy relative to the Sun to escape the solar system, even if it had started from rest at the Sun's surface. The planetary deflections it experiences are like trying to stop a freight train by throwing ping-pong balls at it. Measurable in principle, but irrelevant in practice. N-body simulations, computer models that track the gravitational influences of all planets, simultaneously confirm these predictions. When you run the trajectory of 3 Atlas forward or backward through time, accounting for every planetary perturbation, the result is consistent. A hyperbolic approach, a brief solar system passage, and a hyperbolic departure. The historical context provides reassurance through familiarity. 1 Oumuamua followed a similar hyperbolic trajectory during its 2017 visit. 2 Borisov did the same in 2019 and 2020. The pattern is consistent. Interstellar objects visit, provide scientific opportunities, and depart without drama. But there is an important difference in public perception. Both previous interstellar visitors were discovered relatively late in their passages. Their trajectories were already well established, and their departure was imminent. 3 Atlas was found earlier in its approach. This provided more time for observations, but also more time for speculation and misunderstanding. The flirtation with Mars, occasionally mentioned in early reports, deserves a clarification. The orbit of 3 Atlas does carry it through the general region of Mars orbital distance, but Mars will not be anywhere near that location when the comet passes through. It is like saying 2 cars will collide because their routes cross the same intersection, but ignoring the fact that they will arrive hours apart. Even if Mars and 3 Atlas were to approach each other more closely, which they will not, the gravitational interaction would be insignificant. Mars has only 11% of Earth's mass, and a far lesser gravitational influence than Jupiter, which has already been accounted for in the trajectory calculations. The mathematics of orbital mechanics leave no room for surprise disasters, no hidden dangers or last-minute plot twists. The laws of physics that govern 3 Atlas are the same ones that allow us to navigate spacecraft to distant planets, to predict eclipses centuries in advance, and to maintain GPS satellite constellations with meter-level accuracy. When scientists say that 3 Atlas poses no threat to Earth, they are not making a guess. They are not offering a professional opinion. They are stating a mathematical certainty, one based on fundamental physical laws that have been tested and verified countless times over centuries. The real mystery is not whether 3 Atlas is dangerous. It is not. The real mystery is what this ancient traveler can teach us about how worlds form around other stars, what materials were common in the early galaxy, and how planetary systems across the cosmos build themselves from dust and gravity. The distance measurements in astronomical units and mass ratios expressed in scientific notation might seem abstract, but they represent the difference between a rational assessment and an irrational fear. 3 Atlas is fascinating because it is safe to study, not despite being safe to study. Sunlight, a solar wind, and the coma. Picture an ancient iceberg older than the Earth itself awakening after millions of years of a deep freeze. As 3 Atlas draws closer to the Sun, something remarkable begins to happen. The sparse starlight that has warmed its surface for eons suddenly intensifies. It becomes the focused energy of our solar system's central furnace. This is the moment when a dark frozen wanderer transforms into an active comet. The physics are elegantly simple. Sunlight carries energy, and that energy heats whatever it touches. As 3 Atlas approaches, perihelion solar heating penetrates its surface layers. This causes frozen materials to sublimate, transforming directly from ice to vapor without passing through a liquid phase. This outgassing process creates the characteristic coma, the extended atmosphere of gas and dust that makes comets visible across vast distances. But 3 Atlas is not following the typical script. Most comets in our solar system are dominated by water ice. When they approach the Sun, water sublimation creates the bulk of their coma and tail. Carbon dioxide, carbon monoxide, and other compounds contribute. But water usually takes the lead role in the outgassing drama. The James Webb Space Telescope revealed something different. 3 Atlas shows unusually strong carbon dioxide emissions compared to water. Early estimates suggest a ratio approaching 8:1. This is not just unusual, it is a complete inversion of what we normally see. The SPHERE-X mission added another piece to the puzzle. Its wide-field spectral observations mapped the carbon dioxide coma. A coma extending for hundreds of thousands of kilometers, nearly the distance from Earth to the Moon. Meanwhile, water and carbon monoxide emission, which should announce themselves clearly in this spectral range, were conspicuously absent. These are preliminary results, the kind that make scientists excited and nervous simultaneously. The teams analyzing this data are still refining their measurements, still double-checking their instruments, and still making sure they are not seeing instrumental artifacts or calibration errors. But if these observations hold up under scrutiny, they point towards something genuinely extraordinary. The carbon dioxide dominance suggests several possibilities, each with intriguing implications. Perhaps 3 Atlas was formed in the outer reaches of its birth system, beyond the carbon dioxide ice line where carbon dioxide freezes before water does. This would place its origin in a region analogous to our outer asteroid belt or beyond, in the cold dark zones where only the most volatile materials remain gaseous. Alternatively, 3 Atlas might have developed a surface crust that acts like a selective valve, allowing carbon dioxide to escape while trapping water beneath. Think of it as a cosmic permafrost, an outer layer that insulates the interior and controls which materials can sublimate under solar heating. Both scenarios challenge our standard models of how outer protoplanetary disks distribute their chemical inventory. We are not just looking at one oddball comet, we are potentially glimpsing an entirely different approach to volatile chemistry in planetary formation. The dust production mechanics become particularly interesting when carbon dioxide leads the outgassing process. Water vapor has specific properties when it comes to lifting and accelerating dust particles away from a comet's nucleus. carbon dioxide behaves differently, with different expansion rates, different cooling properties, and different abilities to entrain solid particles. This means the tail morphology and brightness evolution of 3 Atlas might not follow familiar patterns. The dust distribution might be different, the particle size ranges might be unusual, and the overall appearance in telescopic images might challenge expectations based on water-dominated comets. Visibility expectations need to be managed carefully here. Despite its chemical activity, 3 Atlas will not necessarily put on a spectacular show for casual observers. The geometry of its passage places it behind the sun's glare during peak activity. This makes Earth-based observations challenging precisely when the comet is most active. This timing creates a natural experiment in comparative comet science. We can observe 3 Atlas during its approach, lose sight of it during solar conjunction, and then pick up observations again as it recedes from the sunday. The before and after comparison will reveal how perihelion passage affects its composition, its outgassing rates, and its dust production. Spacecraft positioned throughout the solar system fill the observation gap during solar conjunction. The Mars orbiters can watch the comet's behavior when Earth-based telescopes are blinded by solar glare. This multi-platform approach provides unprecedented coverage of a comet's complete passage through the inner solar system. The comparison with typical solar system comets illuminates just how unusual 3 Atlas appears to be. Most comets show water emission lines dominating their spectra near 1 astronomical unit from the sunday. They produce predictable ratios of different molecular species. They follow well-understood patterns of brightness, variation, and tail development. 3 Atlas seems to be writing its own rules. Grain size analysis from ongoing studies will reveal whether carbon dioxide, dominated outgassing, produces different dust characteristics, different than water-dominated systems. Larger grains, smaller grains, different mineral compositions, and unusual shapes. All these factors could distinguish interstellar dust from solar system dust in ways we are only beginning to understand. Gas velocity measurement adds another layer of complexity. Different molecular species sublimate at different rates and expand away from the nucleus at different speeds. Carbon dioxide has different thermodynamic properties than water. This could create different pressure gradients, different expansion patterns, and different interactions with the solar wind. Fragmentation likelihood becomes a relevant concern as solar heating intensifies. Some comets break apart under thermal stress, especially if they have a weak internal structure or contain materials with different expansion coefficients. The unusual composition of 3 Atlas might make it more or less susceptible to fragmentation, a question that can only be answered through careful monitoring. The multiple apparitions across the solar conjunction gap will provide crucial data about temporal evolution. How does the comet's behavior change as it approaches perihelion? How does it respond to peak solar heating? And how does its activity decline as it recedes toward interstellar space? The tri-panel imaging from the JWST offers a template for understanding molecular distribution. Total flux shows an overall activity level. The 4.3 micrometer channel highlights carbon dioxide emission, and the 2.7 micrometer channel reveals water emission. The contrast between these channels tells the story of the unusual chemistry of 3 Atlas. For public outreach, the carbon dioxide coat analogy helps to explain why some comets behave differently. Just as different planets have different atmospheric compositions, different comets carry different chemical signatures that reflect their formation environments and evolutionary histories. The caveat about compositional ratios bears repeating. These measurements will be refined as peer review proceeds and analysis techniques improve. What we are seeing now represents the first draft of the chemical story of 3 Atlas, not the final version. But even as preliminary results, These observations are reshaping our understanding of volatile chemistry in planetary formation. They suggest that the processes that build worlds around other stars can produce very different outcomes. Outcomes different from our solar system's template. They hint that interstellar space might be populated by a diverse collection of chemical signatures, each one telling a unique story about planetary formation under different conditions. The awakening of 3 Atlas under our Sun's influence is not just about one comet's behavior. It is about the diversity of outcomes possible when gravity, chemistry, and time collaborate to build worlds, to build them around the stars throughout the galaxy. Can we go to meet it? The realistic investigation paths. The romantic notion of launching a spacecraft to rendezvous with 3 Atlas captures our imagination. A race across the solar system to shake hands with a visitor from another star. Unfortunately, the mathematics of orbital mechanics and spacecraft engineering are less romantic than our ambitions. The brutal constraints are straightforward. 3 Atlas is traveling at approximately 57 kilometers per second relative to the Sunday. It was discovered in July of 2025. This gives us roughly 3 to 4 months before perihelion passage. Even our fastest spacecraft take years to reach the outer solar system, and that is when we can plan trajectories carefully and launch at optimal times. Building and launching a dedicated intercept mission would require capabilities that exist only in science fiction. We would need a spacecraft that could accelerate to unprecedented velocities, one that could survive the radiation environment near the Sunday, and that could somehow match course with an object moving faster than anything we have ever attempted to intercept. But here is the beautiful thing about modern space exploration. We do not need to build new missions to conduct extraordinary science. We just need to be clever about using the assets we already have positioned throughout the solar system. The geometry of 2025 creates some remarkable opportunities. Several major spacecraft find themselves in advantageous positions during the passage of 3 Atlas, not through careful planning, but through the fortunate alignment of mission timelines and orbital mechanics. The ESA's JUICE mission, the Jupiter Icy Moons Explorer, completed its Venus gravity assist on August 31st. This placed it in an excellent position for 3 Atlas observations at approximately 68 million kilometers from the comet during key observation windows. JUICE carries sophisticated cameras and spectrometers that could provide unprecedented close-up views of an interstellar visitor. NASA's Psyche spacecraft, en route to study a metallic asteroid, sits roughly 45 million kilometers from 3 Atlas. While Psyche's instruments are optimized for asteroid science rather than comet observation, they could still capture valuable data about the comet's activity and dust environment. Perhaps most intriguingly, the Mars Orbiter constellation finds itself perfectly positioned for 3 Atlas observations. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1 mission, and the UAE's Hope Orbiter all enjoy front-row seats. They are at distances of just 29 million kilometers from the comet. These are not purpose-built comet missions. They are existing spacecraft with their own primary objectives, their own carefully planned observation schedules and scientific priorities. But the fortunate alignment of orbits creates opportunities for multi-platform observations that would have been impossible to plan deliberately. The advantages of spacecraft observation become crucial around perihelion. This is when Earth's view of 3 Atlas becomes severely compromised by solar glare. While ground-based telescopes lose sight of the comet when it is most active, and scientifically interesting spacecraft positioned throughout the solar system do not face this limitation. They can maintain clear lines of sight to 3 Atlas throughout its passage, watching the tail develop, monitoring outgassing behavior, and potentially sampling a dust particle if orbital mechanics aligns favorably. The measurement possibilities depend on each spacecraft's instrument complement, Imaging systems can track morphological changes in the coma and tail. Spectrometers can analyze the chemical composition of the outgassing materials. Dust detectors can characterize particle sizes and impact rates if the spacecraft passes through extended dust environments. These observations are not guaranteed, they are opportunistic. Spacecraft instruments are not necessarily optimized for comet science, and primary mission requirements always take priority. Mission planners must balance the scientific value of 3 ATLAS observations against the needs of primary mission objectives. But even modest resolution imaging and basic spectroscopy from these platforms could provide invaluable data. Data about how an interstellar comet behaves when it is impossible to observe from Earth. The heliophysics community offers additional observational platforms. The Solar and Heliospheric Observatory, the Parker Solar Probe, and the upcoming Punch mission all have specialized instruments. Instruments designed to study the solar wind and space weather environment. These spacecraft could observe the interaction of 3 ATLAS with solar particles and magnetic fields. This would provide insights into how interstellar material responds to our Sun's influence. Risk management becomes a crucial consideration for any spacecraft observation. Direct fly-throughs of comet tails, while scientifically valuable, expose spacecraft to potential damage from high-velocity dust impacts. Mission planners must weigh scientific opportunity against hardware protection. Especially for spacecraft with ongoing primary missions worth hundreds of millions of dollars, passive sensing from safe distances offers the optimal balance of scientific value and operational safety. Spacecraft can observe 3 ATLAS from thousands or tens of thousands of kilometers away. This is well outside any dust hazard zones while still collecting scientifically valuable data. The data choreography requires careful coordination across multiple space agencies and mission teams, timing observations to complement each other, sharing data rapidly for cross-validation, and coordinating instrument settings for maximum scientific return. All these factors require diplomatic finesse and technical precision. The before and after comparisons become particularly valuable when combining Earth-based observations with spacecraft data. Ground telescopes can characterize 3 ATLAS during its approach. Spacecraft fill the observation gap during solar conjunction, and ground telescopes resume monitoring as the comet emerges from behind the Sun's glare. This coordinated approach provides unprecedented coverage of a comet's complete passage through the inner solar system. It reveals how perihelion passage affects composition, activity level, and dust production, reveals it in ways that single-platform observations cannot match. Citizen engagement remains possible even without a dedicated spacecraft mission. Public webcasts of observing sessions and real-time data sharing allow public participation. So do citizen science projects for image processing and data analysis. All allow the public to participate directly in cutting-edge research. Ground-based facilities like the Gemini Observatory and Noir Lab have demonstrated the public appetite for live observing sessions during previous interstellar visitor passages. These events combine education with entertainment, allowing people worldwide to watch professional astronomers conduct real research in real time. The bottom line is both disappointing and encouraging. We cannot launch a Hollywood-style intercept mission to 3 ATLAS. The physics and timing simply do not work. But clever coordination of existing spacecraft and ground-based facilities can provide scientifically rich observations that might be even more valuable than a single dedicated mission. This approach represents the future of space science in an era of routine interstellar visitors. Instead of building expensive, bespoke missions for each target, we maintain a constellation of capable spacecraft and ground-based facilities that can rapidly pivot to study unexpected opportunities. 3 Atlas is testing this coordinated approach in real time, demonstrating whether distributed observation networks can match the scientific return of traditional flagship missions, while maintaining the flexibility to respond to targets discovered with little advanced warning. The results will inform how we prepare for the next interstellar visitor and the one after that. As these cosmic travelers transition from rare curiosities to routine scientific opportunities, what it teaches us about other suns. Every piece of cosmic debris tells a story about where it came from. But 3 Atlas might be carrying one of the oldest stories ever delivered to our scientific instruments. Preliminary evidence suggests we are looking at material that predates Earth's formation, a geological sample from the galaxy's youth when the universe was fundamentally different than it is today. The kinematic evidence is tantalizing, but it is still under debate. Several analyses of the motion of 3 Atlas through space suggest it originated in the Milky Way's thick disk, a population of older metal-poor stars formed during the galaxy's early history. If this interpretation holds up, we are examining material that is at least 7 billion years old, and possibly much older. To understand why this matters, we need to think about how the galaxy builds itself over cosmic time. Stars form in waves, with different generations using different raw materials and following different patterns of chemical evolution. The thick disk represents stars formed during cosmic noon, the peak era of star formation when the universe was roughly half its current age, and galaxies were busy assembling themselves from smaller components. But the kinematic story is not settled. A competing analysis using data from the Gaia Space Telescope suggests something else. It suggests 3 Atlas might have originated in the thin disk, a younger population of stars with near-solar metallicity. This implies a more recent origin in a star system much like our own. This disagreement is not a failure of science. It is science working as designed. Different teams using different analysis techniques and different data sets are testing each other's results, refining measurements and gradually converging on the truth. The process takes time, but it produces reliable answers. The chemical composition adds crucial evidence to this cosmic detective story. The carbon dioxide-rich nature of 3 Atlas points toward a specific formation, a formation beyond the carbon dioxide ice line in its parent star system, or under specific irradiation conditions that favor carbon dioxide retention over water ice preservation. These chemical signatures are like fingerprints from exoplanetary nurseries that we will never visit directly. When planetary systems form, they scatter leftover planetesimals throughout interstellar space. Planetesimals are chunks of rock, metal, and ice. These ejected building blocks carry the chemical signatures that sample the materials available in their birth environments. The exoplanet connection deserves emphasis. Every interstellar comet represents a piece of a failed planet, a chunk of material that almost became part of a world, but was instead ejected during the chaotic early phases of planetary system formation. By studying these cosmic refugees, we are essentially conducting archaeology on an exoplanetary formation process. If 3 Atlas truly originated in the thick disk, the implications are staggering. We would be examining material formed when the galaxy was younger, when heavy elements were less common, and when the chemical inventory available for planet formation was significantly different from what we see today. This connects to fundamental questions about planetary formation across cosmic time. Did early planetary systems form differently because they had access to different materials? Were volatiles like water and carbon dioxide distributed differently in primordial disks? And how has the efficiency of planet formation changed as the galaxy has evolved? The comparative interstellar object science is building a catalogue of diversity, a diversity that challenges our solar system's assumptions. 2 Borisov appeared to be water-rich and relatively normal. 1 Oumuamua was so unusual that astronomers still debate whether it was a comet at all. 3 Atlas seems to be carbon dioxide dominated and chemically distinct. This small sample already suggests that interstellar space contains a variety of chemical signatures, each one reflecting different formation, environments, and evolutionary pathways. As our detection capabilities improve and more interstellar visitors are discovered, we are building a census of how the planetary formation process varies across different stellar environments. The discovery rate projections are encouraging. The upcoming Rubin Observatory is expected to find interstellar objects at rates ranging from 1 to a dozen per year. This depends on their actual population density and size distribution. This transition from rare curiosities to routine discoveries will revolutionize interstellar object science. With larger sample sizes, astronomers will be able to perform population studies, looking for correlations between chemical composition and kinematics, between size and activity level, and between orbital characteristic and formation environment. The individual objects like 3 Atlas provide fascinating case studies, but population statistics reveal the underlying physical processes. The thick disk hypothesis, if confirmed, opens a window into a cosmic history that is otherwise inaccessible. We can study the oldest stars in our galaxy, but their surfaces do not preserve information about the conditions in which they were formed billions of years ago. Comets like 3 Atlas might retain that chemical memory in their frozen interiors. This connects to broader questions about cosmic evolution. When did the first planetary systems form? How different were they from modern systems? And what role did early planet formation play in the chemical evolution of the galaxy? These questions require data from the earliest epochs of galactic history, and 3 Atlas might be providing exactly that. The preprint culture in astronomy means we can follow these debates in real time as they develop. Papers appear on the arXiv before peer review, allowing the community to see preliminary results and to begin responding with additional observations or alternative interpretations. This transparent process shows how a scientific consensus develops gradually through a competition between different ideas, but we need to be careful about preliminary results. The thick disk versus thin disk debate will likely continue for months or years, as additional kinematic analyses are completed and chemical composition measurements are refined. Science communication requires clearly distinguishing between provisional findings and established results. The galaxy mapping context helps to visualize what we are discussing. The Milky Way's structure includes several distinct components: a thin disk of young stars like the Sunday, a thick disk of older stars formed during the galaxy's early assembly, a central bulge of ancient stars, and a spherical halo of the galaxy's oldest stellar populations. Each component represents a different era in galactic evolution, with different chemical compositions, different kinematics, and different histories of star and planet formation. If 3 Atlas originated in the thick disk, it is carrying information from an era when the galaxy was still actively growing through mergers with smaller galaxies. The confidence metrics that accompany these analyses deserve attention. Kinematic studies typically provide error bars and statistical significance measures that indicate how reliable the conclusions are. Understanding these uncertainties is crucial for evaluating competing claims about the origin of 3 Atlas. The ultimate payoff extends beyond one comet's biography. If we can reliably determine the galactic origins of interstellar objects, we gain a new tool for studying galactic evolution, stellar populations, and the history of planet formation. A new tool for studying them across cosmic time. 3 Atlas might be more than just a visitor from another star system. It might be a messenger from another era entirely, carrying news from the galaxy's youth about how worlds were built when the universe was fundamentally different. The question is not just where 3 Atlas came from, but when and what that timing reveals about the long history of planets, stars, and galaxies rebuilding themselves from cosmic dust. What it means for us in a near term. The discovery of 3 Atlas represents more than just another entry in the catalogue of interstellar visitors. It is a stress test of our scientific infrastructure, a validation of our survey capabilities, and a preview of how astronomy will function in the coming decade. A decade when such visitors transition from rare curiosities to routine discoveries. The survey upgrade pathway is already clear. The Vera C. Rubin Observatory is scheduled to begin operation in the mid-2020. It will revolutionize our ability to detect and characterize interstellar objects. Current estimates suggest the Rubin could find anywhere from 1 to a dozen interstellar visitors annually. This depends on the actual population density and size distribution of these objects in interstellar space. This dramatic increase in discovery rate will transform interstellar object science from a field driven by individual case studies to one capable of population statistics and comparative analysis. Instead of examining each visitor as a unique specimen, we will begin to see patterns, correlations, and systematic differences that reveal underlying physical processes. The pipeline maturity improvements are already visible. Atlas, the Catalina Sky Survey, and Linear have refined their algorithms for detecting objects with unusual motion characteristics. The rapid identification of 3 Atlas as potentially interstellar demonstrates how these systems have learned from previous discoveries, like 1 Oumuamua and 2 Borisov. Future interstellar visitors will be flagged more quickly, characterized more efficiently, and studied more comprehensively than their predecessors. The learning curve from 3 Atlas will benefit every subsequent discovery, creating a cumulative improvement in our response capabilities. The planetary defense literacy angle deserves particular attention. 3 Atlas provides a perfect teaching moment about uncertainty and measurement precision, and the difference between unknown and dangerous. The object's safe distance and predictable trajectory demonstrate how astronomical calculations work and why they are reliable. This educational opportunity matters because planetary defense depends on public understanding and support. When genuinely hazardous objects are discovered in the future, the public's response will be shaped by their familiarity with how these calculations work, and why scientists can make confident predictions about trajectories and impact risks. Mission planning philosophies are evolving in response to discoveries like 3 Atlas. The Comet Interceptor mission represents a new approach. Instead of launching toward a specific target, a spacecraft is positioned at a gravitationally stable Lagrange point. There it waits for interesting targets to announce themselves. This wait and pounce strategy could become the standard for studying unpredictable targets with short discovery lead times. The career and training implications ripple through the astronomical community. Graduate students and postdocs are gaining experience with rapid response observational campaigns, with multi-facility coordination and international collaboration under time pressure. These skills will be increasingly valuable as transient astronomy becomes more common across multiple subfields. 3 Atlas mobilizes research teams across dozens of institutions and facilities. Students learn to work with data from the JWST Hubble Spherics and ground-based telescopes simultaneously. They practice coordinating observations across time zones and organizational boundaries. They develop expertise in moving target tracking, spectroscopic analysis, and multi-wavelength data fusion. These experiences produce researchers who are comfortable with complexity, uncertainty, and collaboration, exactly the skills needed for 21st century astronomy. The public engagement spillover effects extend far beyond astronomy. Live telescope sessions, citizen science projects, and educational programs around 3 Atlas introduce people to scientific methodology, to international cooperation, and the excitement of discovery. These experiences influence career choices, voting patterns, and public support for scientific research. Educational institutions are incorporating 3 Atlas into lesson plans. Lessons about orbital mechanics, spectroscopy, and scientific methodology. Students learn to distinguish between preliminary results and peer-reviewed findings, between speculation and evidence-based conclusion, and between media hype and scientific reality. The budget implications deserve a realistic assessment. The scientific windfall from 3 Atlas does not require massive new expenditures or congressional appropriations. It primarily represents coordination and scheduling among existing facilities and missions. The most expensive component might be the additional staff time needed for data analysis and paper preparation. This efficiency demonstrates the value of maintaining a diverse, capable scientific infrastructure. Instead of building specialized missions for each target of opportunity, we maintain a portfolio of capabilities that can rapidly pivot to study unexpected discoveries. The return on investment is extraordinary. The next decade roadmap is becoming clear. Improved surveys will detect interstellar objects earlier and more reliably. Better alert systems will notify the global community more quickly. Enhanced coordination protocols will maximize scientific return from limited observing opportunities. Eventually, interceptor missions positioned at strategic locations will provide close-up studies of the most interesting visitors. Each step builds on the lessons learned from current discoveries. 3 Atlas provides crucial experience with the entire pipeline. From detection to detailed characterization to scientific interpretation, the metric to track is response time. How quickly can the community move from discovery to initial characterization to detailed follow-up observation? 3 Atlas establishes a baseline for this metric that future discoveries should improve upon. A rapid response requires not just better instruments, but better coordination. Data sharing agreements, observing time allocation procedures, and international cooperation frameworks all need refinement. A refinement based on real-world experience with objects like 3 Atlas. Infrastructure investments are largely invisible to the public, but are crucial for scientific success. Better computational resources for orbit determination, improved communication systems for coordinating observations, and enhanced data archiving for long-term studies. These behind-the-scenes improvements determine whether discoveries like 3 Atlas become transformative science or missed opportunities. The competence development aspect deserves emphasis. The real outcome for humanity is not dramatic sky shows or existential threats. It is the gradual development of systematic capabilities for understanding our cosmic environment. We are becoming better at detecting unexpected visitors, at characterizing their properties, at predicting their behavior, and at learning from their compositions. This competence extends beyond interstellar visitors to potentially hazardous asteroids, to solar system exploration and space situational awareness. The techniques developed for 3 Atlas improve our ability to track and understand any small body moving through space. The international collaboration templates being established now will serve as models for future discoveries. When the next interstellar visitor arrives, or when a genuinely hazardous asteroid is discovered, the coordination mechanisms tested on 3 Atlas will provide proven frameworks for a rapid, effective response. Perhaps most importantly, 3 Atlas normalizes the idea that our solar system exists within a larger galactic community. These visitors remind us that planetary formation occurs throughout the galaxy, that other star systems occasionally share their leftovers with us, and that our cosmic neighborhood is more dynamic and interconnected than previous generations had realized. This perspective shift from cosmic isolation to galactic citizenship may ultimately be the most significant contribution of 3 Atlas to human understanding. We are not alone in space, not in the science fiction sense of alien civilizations. but in the deeper sense of participating in the galaxy-wide processes of planetary formation and evolution. The systems we are building to study 3 Atlas prepare us for a future where such discoveries are routine, where interstellar archaeology becomes a standard astronomical discipline, and where humanity's understanding of planetary formation extends far beyond our own solar system's example. The artifact hypothesis, clearly labeled as speculation. Now we enter the realm of speculation, the territory where science fiction meets scientific methodology. Some researchers' blogs and preprint servers have suggested that 3 Atlas might not be a natural comet at all. Could it be artificial? Could it represent technology from another civilization? And could it pose risks beyond simple gravitational mechanics? Let's examine these claims with the same rigorous skepticism we apply to any extraordinary parcellus. Assertion. The artifact hypothesis requires extraordinary evidence because it makes an extraordinary claim. If 3 Atlas were artificial, constructed, or modified by intelligent beings, it would be the most significant discovery in human history. The implications would reshape our understanding not just of our cosmic environment, but of our place in the universe itself. So what evidence would convince scientists that 3 Atlas is artificial rather than natural? The checklist is demanding but clear. Non-gravitational accelerations inconsistent with normal outgassing would be a strong indicator. Natural comets experience slight course corrections as sublimating gases create rocket-like thrust, but these accelerations follow predictable patterns based on solar heating and rotation. Artificial objects might show accelerations that do not match these patterns. An engineered reflectance characteristic would provide another crucial signature. Natural comet surfaces are chaotic mixtures of ice, rock, and organic compounds. They have irregular shapes and random orientations. Artificial surfaces might show geometric patterns, unusual brightness, variations, or reflectance spectra that do not match any known natural material. A coherent radio emission would be perhaps the most definitive evidence. Natural comets do not generate organized radio signals beyond thermal noise and occasional plasma interaction. Artificial objects, especially those designed for communication or navigation, might broadcast structured signals that stand out clearly against the cosmic background. A controlled maneuver would provide unambiguous proof of artificial origin. Natural objects follow predictable trajectories determined by gravity and outgassing forces. Artificial objects might demonstrate course corrections, orbital adjustments, or trajectory changes that could not be explained by known physical processes. The current observational evidence for 3 Atlas shows none of these artificial signatures. The JWST observations reveal classical molecular emission lines from carbon dioxide, lines consistent with normal cometary outgassing. The Hubble Space Telescope shows a typical teardrop-shaped dust coma, a coma that matches theoretical predictions for natural comets under solar heating. The SpherX mapping reveals extended carbon dioxide envelopes that follow the expected patterns for gas expansion in the vacuum of space. Radio telescopes have monitored 3 Atlas for any unusual emission. The searches have revealed thermal radiation consistent with a cold object warming under solar heating, but no structured signal, no coherent transmission, and no evidence of artificial radioactivity. Astrometric measurements, precise tracking of the object's position over time, show trajectory changes consistent with natural outgassing. The slight accelerations observed match theoretical predictions for carbon dioxide sublimation from a rotating nucleus. There is no evidence of a controlled maneuver or artificial course correction. The media literacy component becomes crucial when evaluating artifact claims. Provocative blog posts and speculative articles spread faster through social media than careful scientific analysis. The attention-grabbing headline, "Could an interstellar visitor be an alien probe?" generates more clicks. more clicks than spectroscopic analysis, confirms natural comet composition. This is not a conspiracy or a cover-up. It is the natural consequence of how information spreads in the internet age. Sensational possibilities travel faster than mundane realities, regardless of their scientific merit. The dark forest hypothesis, popularized by science fiction author Liu Cixin, suggests something. That hostile civilizations might send artificial objects to scout or attack other worlds. This makes for compelling storytelling, but it requires evidence beyond the realm of current observations. Science fiction scenarios are worth considering as thought experiments, but they belong in the entertainment category until evidence elevates them to a scientific hypothesis. There is nothing wrong with speculation, as long as it is clearly labeled as such and does not masquerade as an established fact. How would the scientific community test an artificial origin hypothesis if evidence emerged? The protocols are already in place. Radio SETI organizations maintain arrays specifically designed to detect artificial signals. Radar installations can probe objects for unusual structural characteristics, and precise astrometry can detect controlled maneuvers that violate natural orbital mechanics. The thresholds for changing scientific consensus about 3 Atlas are high but achievable. A single unexplained radio signal might trigger additional observations but would not constitute proof. Multiple independent detections of structured transmissions confirmed by different facilities using different techniques would be much more convincing. Similarly, one anomalous trajectory measurement might indicate an instrumental error or unknown outgassing behavior. A pattern of controlled maneuvers observed by multiple tracking stations over extended periods would be much harder to explain. Much harder to explain through natural processes. The evidence ladder provides a framework for evaluating an extraordinary claim. Rumors and speculations occupy the bottom rung. Preprint papers that have not undergone peer review represent preliminary findings. Findings that might or might not survive scrutiny. Peer-reviewed papers that have survived expert examination carry much more weight. A scientific consensus emerges when multiple independent research groups reach similar conclusions using different methods. The 3 Atlas artifact claims currently occupy the bottom rungs of this ladder. They represent speculation and preliminary suggestions rather than established scientific findings. The Oumuamua case study provides a historical context for how these debates evolve. When one Oumuamua was discovered in 2017, it prompted speculation about an artificial origin. Its unusual elongated shape and slight non-gravitational acceleration were the cause. Some researchers suggested it might be a solar sail or a probe from another civilization. Over time, additional observations and theoretical work provided natural explanations for its unusual characteristics. The current scientific consensus favors a natural origin, though some uncertainty remains about the specific mechanisms responsible for its behavior. This pattern reflects how science processes an extraordinary claim. Initial speculation is followed by a gradual convergence toward natural explanations. The system is designed to be skeptical of dramatic assertions, while remaining open to genuine evidence when it appears. The guardrail against ridicule deserves emphasis. Curiosity about artificial origin is not inherently unscientific. SETI research techno-signature studies and searches for evidence of technological civilizations are legitimate scientific disciplines. The key is channeling curiosity into testable predictions rather than unfounded assertions. Good science distinguishes between "we do not have evidence for this" and "this is impossible." The absence of evidence for an artificial origin does not prove that 3 Atlas is natural. It just means the artifact hypothesis lacks supporting data. If compelling evidence of an artificial origin did emerge, and to be clear, current observations strongly suggest it will not, The implications would apocalyptically alter human civilization's understanding of its cosmic context. Discovery protocols for such a scenario already exist. The International Academy of Astronautics maintains guidelines for announcing potential extraterrestrial contact. The scientific community has procedures for verification, confirmation, and public communication of an extraordinary discovery. But an extraordinary claim requires extraordinary evidence, and that evidence simply does not exist for 3 Atlas. Every observation to date supports a natural comet origin. The chemical signatures, physical behavior, and trajectory characteristics all match theoretical predictions for interstellar comets. The outcome framing helps to maintain perspective. If artifact evidence somehow emerged, which current data strongly argues against it, would indeed be the most significant discovery. The most significant discovery in human history. Absent such evidence, 3 Atlas remains a scientifically treasured comet. One that is expanding our understanding of the planetary formation process across the galaxy. Speculation serves a useful purpose. It highlights the importance of evidence-based reasoning and the scientific method. By examining what evidence would be required to support an extraordinary claim, we better understand how science distinguishes between wishful thinking and reliable knowledge. 3 Atlas offers plenty of genuine mysteries worth exploring without invoking an artificial origin. Its unusual chemical composition, ancient age, and interstellar journey provide more than enough scientific interest, enough to justify careful study. The artifact hypothesis reminds us that the universe is full of possibilities we have not yet discovered. But it also reminds us that distinguishing between possibilities and actualities requires careful observation and rigorous analysis and a healthy skepticism about claims that seem too extraordinary to be true. The hidden message tropes a myth-busting lab. In the age of social media and conspiracy theory, every unusual celestial event becomes a canvas for elaborate speculation. 3 Atlas, with its mysterious origin and unusual composition, has attracted its share of creative interpretations. Let's examine some of the more persistent claims and see how they hold up against actual evidence. The radio signals from the comet narrative represents perhaps the most common type of misinterpretation. Several social media posts have claimed that 3 Atlas is broadcasting structured radio transmissions, potentially indicating artificial intelligence or an alien communication attempt. The reality is more mundane, but also more interesting from a scientific perspective. Radio telescopes have indeed observed 3 Atlas, but they detect only thermal radiation, the natural radio emissions that any cold object produces when warmed by solar heating. These emissions follow predictable patterns based on the object's temperature, its composition, and its rotation rate. The sensitivity limits of current radio observations are well understood. If 3 Atlas were broadcasting at power levels typical of human technology, our radio telescopes would easily detect such signals. The absence of structured emissions does not prove that artificial signals are impossible. It demonstrates that none exist at detectable power levels. A thermal noise consideration matters here. Space is filled with natural radio emissions from stars, galaxies, and cosmic ray interactions. Any artificial signal would need to stand out clearly against this background radiation. Pattern recognition algorithms, specifically designed to identify structured signals, have found nothing unusual in the 3 Atlas observations. A beam shape analysis adds another layer of technical sophistication to the radio searches. Natural thermal emissions spread equally in all directions, while artificial transmissions often show directional preferences. The radio emissions from 3 Atlas show the isotropic characteristics expected from natural thermal radiation. The geometric paths and numerology category of claims deserves special attention because it sounds almost scientific. Some online discussions have suggested that the orbital parameters of 3 Atlas contain hidden mathematical relationships or deliberately chosen geometric patterns that indicate intelligent design. These claims misunderstand how orbital mechanics actually works. The trajectory of 3 Atlas results from gravitational interactions with the Sun and planets. Following Newton's laws of motion with exacting precision, the orbital elements, eccentricity, inclination, and perihelion distance, are determined by the object's velocity and position when it entered the solar system, not by any conscious design process. The hyperbolic orbits for interstellar objects are mathematically inevitable given their high velocities relative to the Sunday. The specific parameters of the orbit of 3 Atlas result from the random direction and speed it carried from its parent star system, a direction modified by billions of years of galactic dynamics. The time to hide at perihelion conspiracy theory misrepresents the geometry of solar system observation. 3 Atlas is not hiding behind the Sunday, it is following a predictable trajectory that happens to place it in solar conjunction during late October. This timing is determined by orbital mechanics, not strategic planning. The comet's approach trajectory and Earth's orbital position combine to create the observation geometry. Spacecraft positioned throughout the solar system will maintain clear views of 3 Atlas during the conjunction period. This provides a continuous monitoring capability. Solar conjunction is a common occurrence for objects orbiting the Sunday. Mars experiences a superior conjunction approximately every 26 months. Venus goes through conjunction phases regularly. These geometric alignments are the natural consequences of orbital motion, not evidence of a concealment attempt. Reproducible verification methods are crucial for evaluating these claims. Anyone can track updates on NASA's official 3 Atlas webpage. It provides regular updates on orbital parameters, observation schedules, and scientific results. The ESA maintains similar resources for JWST observations and European spacecraft monitoring. Date stamps and version tracking allow interested parties to see how measurements evolve as more observations become available. Initial orbital estimates get refined as the observation arc lengthens. Preliminary composition measurements get updated as spectroscopic analysis improves. This transparent process demonstrates how scientific knowledge develops through accumulated evidence. Open data policies ensure that interested researchers worldwide can access the raw observations. Hubble Space Telescope images become publicly available through the Space Telescope Science Institute archives. NORLab press releases include both processed images and technical details about observation methods. JWST spectra and analysis results are shared through the Space Telescope European Coordinating Facility. The claim versus check methodology provides a template for evaluating an extraordinary assertion. When someone claims that 3 Atlas shows unusual behavior, interested parties can check the current NASA updates. They can compare with official orbital predictions, and they can verify whether the observations match the claims. A URL verification helps to distinguish between reliable sources and speculative websites. NASA, the ESA, and major observatories maintain official domains with consistent formatting and citation practices. These sources provide technical details, error bars, and acknowledgements of uncertainty where appropriate. Scientific uncertainty requires careful communication. Preprints posted to the arXiv represent preliminary research that has not undergone peer review. These papers can contain valuable insight, but may also include errors or interpretations that do not survive expert scrutiny. The arXiv's identifier system allows tracking of paper versions and subsequent publications in peer-reviewed journals. The peer review process serves as quality control for scientific claims. Papers accepted by journals like Astronomy and Astrophysics, the Astrophysical Journal, or Nature have survived expert examination. Examination by researchers familiar with the relevant analysis techniques and observational methods. Reading spectroscopic data requires some technical background but follows consistent principles. The 4.3 micrometer spectral line indicates carbon dioxide emission. The 2.7 micrometer region reveals water vapor. The relative strengths of these features tell the story of the unusual composition of 3 Atlas. A detection versus non-detection distinction matters enormously in spectroscopic analysis. A clear spectral line at the expected wavelength constitutes a positive detection. Noise at that wavelength or signal levels below instrumental sensitivity represents a non-detection, not evidence for an absence. The live observing session invitations provide opportunities for public engagement with actual research. Major observatories occasionally offer webcasts during significant observations, allowing viewers to watch professional astronomers conduct real research in real time. These sessions demonstrate the methodical, careful nature of astronomical observation. The image release schedules follow predictable patterns for major facilities. Hubble typically processes and releases significant images within days or weeks of an observation. The JWST follows similar timelines for high-priority targets. Ground-based observatories often provide same-night availability for exceptional events. Comparison exercises help to develop critical thinking skills. By examining multiple interpretations of the same data, viewers learn to distinguish. They learn to distinguish between evidence-based conclusions and speculative extrapolations. Scientific literacy develops through practice in evaluating competing claims against available evidence. The educational value of myth-busting extends beyond 3 Atlas to general scientific literacy. Learning to identify reliable sources, to understand uncertainty, quantification, and to distinguish between correlation and causation, these provide the tools for evaluating all kinds of technical claims. The invitation to direct participation concludes our myth-busting session. Rather than simply accepting or rejecting claims about 3 Atlas, interested parties can engage directly with the observational process. They can follow along with live observing sessions, examine the archived data, and compare their interpretations with expert analysis. This participatory approach transforms passive consumers of science news into active participants in the scientific process. The tools exist, the data are available, and the methods are transparent. The only requirement is the willingness to engage with evidence rather than speculation. 3 Atlas offers genuine scientific mysteries worth exploring through careful observation and rigorous analysis. The hidden message we should take from this cosmic visitor is not encoded in radio signals or geometric conspiracies. It is written in the spectral lines and orbital mechanics that reveal the authentic story of an ancient traveler from another star. The Mars rendezvous fantasies, and why they do not pencil out. The human imagination, when confronted with cosmic visitors, tends toward the grandiose. Social media buzzes with elaborate scenarios. Redirect 3 Atlas to seed Mars with water and organic compounds. Use gravitational assists to crash it into Mars and thicken the atmosphere, and fragment it into a ring system that could transform the red planet's climate. These ideas capture our desire to play cosmic engineer, but they founder on the unforgiving mathematics of orbital mechanics and spacecraft engineering. Let's start with the energy requirements, because energy is the universal currency that determines what is possible and what is a fantasy in space operations. 3 Atlas is traveling at approximately 57 kilometers per second relative to the Sunday. This represents an enormous amount of kinetic energy, roughly 10 to the 21st power joules. This assumes a conservative nucleus mass estimate. For comparison, the total energy output of all human civilization in a year is about 6 times 10 to the 20th power joules. Redirecting 3 Atlas would require changing its velocity by tens of kilometers per second. a delta-V requirement that exceeds anything humanity has ever attempted by orders of magnitude. Our most powerful rockets can barely achieve delta-V values of 15 to 20 kilometers per second from Earth's surface, and that is when starting from rest, not when trying to alter the trajectory of an object already moving at interstellar speed. The timing constraints make these scenarios even more impossible. 3 Atlas was discovered in July of 2025. This provided roughly 3 to 4 months before perihelion passage. Even if we possess technology capable of delivering the required energy, which we do not, there would not be enough time to design, build, launch, and intercept the comet. Previous spacecraft missions to comets have required years of careful planning and precise trajectory calculation. Deep Impact took 6 years from conception to asteroid impact. Rosetta took 10 years to reach comet 67P, divided by Churyumov-Gerasimenko. These missions targeted predictable slow-moving objects in the outer solar system, not high-speed interstellar visitors discovered months before closest approach. The mass reality check provides another dose of sobering mathematics. Even generously assuming 3 Atlas has a 5-kilometer radius and typical comet density, its total mass would be roughly 10 to the 14th power kilograms. This sounds massive in human terms, but it is utterly negligible compared to planetary scales. Mars has a mass of about 6.4 times 10 to the 23rd power kilograms. That is roughly 6 billion times more massive than our generous estimate for 3 Atlas. The gravitational influence of such a small object on a planet would be so minimal as to be unmeasurable, not even by our most sensitive instruments. The atmospheric seeding fantasy assumes that crashing 3 Atlas into Mars would thicken the atmosphere, or that it would provide useful quantities of water and organic compounds. But the mathematics are unforgiving here too. The atmosphere of Mars has a mass of roughly 2.5 times 10 to the 16th power kilograms. Even if 3 Atlas were pure carbon dioxide, which it is not, and even if all its mass could somehow be converted to atmospheric gas, which it could not, the atmospheric mass increase would be less than 1%. The water delivery scenario fares no better. Mars already contains substantial water reserves in its polar ice caps and subsurface deposits. The amount of water that might be contained in the nucleus of 3 Atlas, even assuming optimistic estimates, it would represent a tiny fraction of Mars' existing water inventory. The ring system proposal demonstrates a fundamental misunderstanding of how planetary rings form and persist. Saturn's rings exist because they are composed of countless small particles in stable orbits. Orbits within the planet's gravitational influence. Creating artificial rings around Mars would require not just fragmenting 3 Atlas itself, a monumental engineering challenge, but also precisely placing those fragments in stable orbits with appropriate spacing and dynamics. Moreover, ring systems do not significantly affect planetary climates. Saturn's rings, despite their spectacular appearance, have a negligible influence on the planet's atmospheric dynamics or its energy balance. Mars rings created from the fragments of 3 Atlas would be beautiful but climatologically irrelevant. The gravitational assist scenarios reveal another layer of impracticality. Some proposals suggest using the gravity of Mars to redirect 3 Atlas towards specific targets or trajectories. But gravitational assists work by exchanging momentum between a spacecraft and planets, and the momentum exchange depends on the relative masses involved. Mars could indeed slightly deflect the trajectory of 3 Atlas through a gravitational interaction, but the effect would be measured in meters per second, not kilometers per second. The fundamental hyperbolic character of the orbit would remain unchanged. 3 Atlas would still escape the solar system, just along a slightly different trajectory. The Mars orbiter science opportunities, however, are genuinely realistic and scientifically valuable. NASA's Mars Reconnaissance Orbiter, China's Tianwen-1 and the UAE's HOPE mission will be excellently positioned to observe 3 Atlas from distances of roughly 29 million kilometers during its passage. These spacecraft carry sophisticated cameras, spectrometers, and other instruments originally designed for Mars observation that could provide unprecedented views of an interstellar visitor. These observations would be scientifically valuable without requiring any redirection manipulation or engineering intervention. The sci-fi storyboard versus real constraint comparison illustrates the gap between imagination and possibility. Science fiction scenarios typically ignore the energy requirements, timing constraints, and engineering limitations that dominate real space operations. They assume technologies that do not exist and capabilities that violate fundamental physics. Real space missions succeed through careful planning, conservative engineering, and realistic goal setting. The most spectacular achievements result from decades of methodical development and incremental progress. Landing rovers on Mars, flying helicopters on alien worlds, and taking pictures of black holes, not from sudden technological breakthroughs or massive energy deployments. Historical precedent supports this reality check. Previous proposals for dramatic redirections of asteroids and comets have consistently failed feasibility analysis. The energy requirements exceed available technology by factors of thousands or millions. The timing constraints are incompatible with human development cycles. The engineering challenges multiply beyond any reasonable solution. One Oumuamua generated similar grand proposals during its 2017 visit. None of them proved to be technically feasible within the constraints of discovery timing and available technology. 2 Borisov inspired comparable speculations during its 2019 to 2020 passage. Again, the practical limitations overwhelmed the ambitious concepts. An opportunity cost consideration matters for actual spacecraft observation. Even a modest redirection attempt would consume enormous resources, and it would likely interfere with the primary missions of spacecraft that could otherwise conduct valuable scientific observation. The Mars orbiters have carefully planned observation schedules designed to maximize scientific return from their primary missions, diverting instrument time and operational resources toward 3 Atlas represents a trade-off that mission planners must evaluate against other scientific priorities. The back-of-the-envelope delta-V calculation that viewers can perform themselves demonstrates the scale of these energy challenges. Delta-V equals the natural logarithm of the mass ratio times the exhaust velocity. Changing the velocity of 3 Atlas by even 10 kilometers per second would require exhaust masses many times larger than the comet itself. This calculation assumes perfect efficiency and ignores practical constraints like propulsion system mass structural limitations and guidance requirements. A real spacecraft redirection would require even more energy than these theoretical minimums suggest. The fantasy sequence conclusion acknowledges that these grand scenarios make entertaining thought experiments. While remaining physically impossible, there is value in imagination and speculation. As long as they are clearly distinguished from a realistic engineering assessment, the return to practical science offers a more satisfying and achievable goal. Understanding the composition of 3 Atlas, tracking its outgassing behavior, and learning from its chemical signatures provide genuine scientific advancement, all without requiring impossible engineering feats. The universe provides enough authentic wonder and genuine scientific opportunities. We do not need to invent fictional capabilities to make them interesting. The sun-triggered catastrophes, why a tiny comet cannot wake the Sunday fear, has a peculiar relationship with scale. A tiny spider can terrify someone who remains calm during thunderstorms. A small asteroid can inspire panic, while massive hurricanes are treated as routine weather. 3 Atlas, despite its genuinely insignificant size compared to the Sun, has sparked concerns. Concerns about triggering solar flares coronal mass ejections, or other solar catastrophes that could threaten Earth. These fears misunderstand the Sun's fundamental nature and the energy scales involved in solar activity. The Sun is a massive self-sustaining nuclear fusion reactor. With a mass of approximately 2 × 10⁻³ kilograms, it generates energy through hydrogen fusion at its core, producing roughly 4 × 10⁻26 watts of power continuously. This energy output has remained remarkably stable for billions of years, varying by less than 1% over time, scales relevant to human civilization. Solar flares and coronal mass ejections result from complex magnetic field interactions within the Sun's atmosphere. These phenomena involve a magnetic energy storage and release process, a process that operates on scales vastly larger than any small comet could influence. The energy comparison reveals the absurdity of the Sun-triggering scenarios. A typical large solar flare releases roughly 10 to the 25th power joules of energy. That is about 6 times more energy than all of human civilization produces in a year. The total kinetic energy of 3 Atlas moving at 57 kilometers per second is roughly 10 to the 21st power joules. This assumes generous mass estimates. This means a single solar flare releases 10,000 times more energy than 3 Atlas carries in its entire motion. The comet is like a firefly trying to influence a volcanic eruption. The scales are so mismatched that a meaningful interaction is impossible. The magnetic field consideration adds another layer of physical impossibility. Solar flares result from a magnetic field line reconnection event in the Sun's corona. These magnetic fields are generated by the Sun's internal dynamo processes, and they are shaped by plasma flows within the solar atmosphere. 3 Atlas has no significant magnetic field of its own, and it carries no mechanism for injecting magnetic flux into the solar system. Cometary material consists primarily of ice, rock, and organic compounds, none of which can meaningfully interact with the Sun's magnetic field structure. The distance factors make a solar influence even more implausible. 3 Atlas reaches perihelion at approximately 1.4 astronomical units, roughly 210 million kilometers from the Sun's surface. At this distance, the comet subtends an angular size smaller than a pixel in most solar observations. The Sun's corona extends millions of kilometers into space, but even the most generous estimates of coronal extent do not reach anywhere near the closest approach distance of 3 Atlas. The comet passes through interplanetary space, not through any component of the Sun's atmospheric structure. Correlation versus causation represents a crucial distinction, a distinction often misunderstood in discussions of comet-solar activity relationships. Comets frequently appear in solar observatory images, particularly those taken by the Solar and Heliospheric Observatory, which maintains a constant watch on the Sun's environment. These appearances create visual associations between comets and solar activity that have no causal foundation. When a comet appears in a SOHO image on the same day that a solar flare occurs, the timing is purely coincidental. The two events are unrelated phenomena that happen to be captured by the same instrument. The SOHO database contains thousands of comet observations, spanning more than 2 decades of solar monitoring. Statistical analysis of this database shows no correlation between comet passages and increased solar activity. If comets triggered solar flares, this correlation would be clearly visible in the data. The energy injection mechanism provides the most fundamental objection to the Sun-triggering scenarios. There is no known physical process by which a small comet could inject sufficient energy into the Sunday energy to trigger flares or coronal mass ejections. Gravitational energy is negligible. The gravitational influence of 3 Atlas on the Sun is orders of magnitude smaller than the tidal effects of Jupiter, which also do not trigger solar activity. Kinetic energy transfer would require a direct impact. But 3 Atlas passes nowhere near the Sun's surface. Material injection through cometary outgassing faces similar problems. The few tons of gas and dust that 3 Atlas releases during its passage represent an utterly trivial addition to the Sun's environment, an environment which processes billions of tons of material through its solar wind every second. The safety assessment for Earth reinforces the lack of a connection between 3 Atlas and solar hazards. The Earth maintains a safe distance of over 270 million kilometers from the comet at closest approach. Solar storm risks remain at normal background levels, levels determined by the Sun's natural 11-year activity cycle rather than any comet influence. Space weather monitoring systems operated by NASA, NOAA, and international partners maintain constant surveillance of solar activity. These systems can predict and track genuine solar storms that might affect satellite operations, power grids, and communication systems. None of these monitoring systems have identified any increased risk associated with 3 Atlas. The coronagraph illusion deserves special attention because it creates compelling but misleading imagery. Solar coronagraphs use occulting disks to block the Sun's bright surface. This reveals the much fainter corona and any objects moving through the field of view. When comets appear in these images, they often seem to be interacting directly with the Sunday. This is because they are visible in the same frame. The visual impression suggests proximity and interaction, but the reality is that the comets are typically millions of kilometers away from the Sun's surface, well outside any region where a meaningful interaction could occur. The dramatic appearance of comets in coronagraph images results from the instrument's design, not from actual proximity to solar phenomena. The occulting disk creates an artificial night sky that makes faint objects visible against the dark background. This creates spectacular imagery that can mislead casual viewers about the actual spatial relationships involved. Heliophysics expert perspectives uniformly dismiss the comet-triggered solar activity scenarios. Researchers who study solar-terrestrial interactions, coronal physics, and space weather have found no credible mechanism by which small comets could influence solar behavior. The scientific literature contains thousands of papers on solar flare triggers and coronal mass ejection initiation, and on magnetic field reconnection processes. None of them identify comets as significant factors in solar activity. The consensus among experts is clear. Comets are passive observers of solar behavior, not active participants. The educational value of addressing these misconceptions extends beyond 3 Atlas. It extends to general scientific literacy about energy scales, cause and effect relationships, and the importance of quantitative analysis. Quantitative analysis in evaluating an extraordinary claim. Understanding why 3 Atlas cannot trigger solar catastrophes helps develop an intuition about astronomical scale and the relative insignificance of small objects in cosmic environments. These concepts apply broadly to other astronomical phenomena, and they help to distinguish between genuine risks and imaginary threats. The SOHO viewing recommendation stands despite the absence of an actual solar interaction. The Solar and Heliospheric Observatory and other solar monitoring spacecraft will capture beautiful images of 3 Atlas, images of it passing through their fields of view during perihelion passage. These images will be scientifically valuable for studying comet tail development and dust distribution. They will be educationally fascinating for demonstrating orbital mechanics, and they will be aesthetically spectacular for their sheer visual appeal. They represent genuine astronomical photography at its finest. Even though they document separate phenomena rather than interacting systems, the conclusion remains that an apocalypse-free reality provides more than enough inspiration for a genuine appreciation of cosmic phenomena. 3 Atlas offers authentic scientific wonder without requiring fictional disasters to make it interesting. The long afterglow culture and science. Every great cosmic event casts two shadows. One is brief and dramatic across the immediate moment. The other is long and subtle across the generations that follow. 3 Atlas, like every significant celestial visitor, before it will leave traces in both scientific archives and cultural memory that persist long after the object itself has disappeared into interstellar darkness. The cultural metamorphosis follows predictable patterns that have repeated throughout human history. Halley's Comet became a harbinger of political upheaval and divine judgment. The Tunguska event spawned a century of speculation about alien visitation and natural catastrophes. Oumuamua inspired both rigorous scientific analysis and elaborate science fiction scenarios about interstellar probes and artificial artifacts. 3 Atlas joins this tradition of cosmic visitors that capture human imagination. Visitors that refuse to be constrained by mere scientific interpretation. Artists will paint its tale against the starfields. Science fiction writers will imagine alien civilizations launching it toward Earth with hidden purposes. And internet communities will develop elaborate theories about its true nature. Theories that persist long after peer-reviewed papers settle the scientific questions. This cultural appropriation is not a failure of science communication. It is an inevitable consequence of how human minds process wonder and uncertainty. Comets become symbols because they represent the vast unknown, the possibility that our assumptions about cosmic order might be wrong, and the tantalizing suggestion that we are not alone in the universe. The scientific afterglow follows different patterns, but it promises a longer-lasting impact. The archives mature over time as calibration techniques improve and analysis methods become more sophisticated. Today's preliminary spectral measurements will become tomorrow's definitive compositional analysis. The current orbital calculations will be refined to extraordinary precision. The initial hypotheses about a formation environment will evolve into detailed models of interstellar chemistry. This maturation process operates on time scales measured in decades rather than months. The Hubble Space Telescope data that seems definitive today will be reanalyzed years from now, reanalyzed using techniques that do not yet exist. The JWST spectra that represent a current state of the art will be superseded by improved calibrations and a better understanding of instrumental systematics. The thick disk versus a thin disk origin debate exemplifies how astronomical controversies develop over extended time scales. Current kinematic analyses suggest different conclusions about the galactic birthplace of 3 Atlas, but these disagreements will be resolved through accumulated evidence rather than a single breakthrough observation. Additional parallax measurements, improved stellar population models, and better galactic dynamics simulations will gradually constrain the possibilities. The resolution might take years, but the eventual consensus will be built on much more solid foundations than current preliminary findings. The composition legacy extends far beyond 3 Atlas itself. It extends to the broader science of interstellar object characterization. The JWST spherics and Hubble data sets establish templates for studying future visitors. The analysis techniques developed for 3 Atlas will be applied to subsequent interstellar comets, with improved efficiency and sophistication. This cumulative improvement in technique and capability represents one of the most important outcomes of the 3 Atlas science. Each interstellar visitor teaches us not just about its own properties, but about how to study the next one more effectively. The survey-era transformation promises to change interstellar object science, from individual case studies to population statistics. The Rubin Observatory's expected discovery rate of multiple interstellar visitors per year will enable comparative studies impossible with current small sample sizes. Population science reveals different insights than individual object studies. The statistical distributions of composition size, activity level, and orbital characteristic will constrain models of the planetary formation process across different stellar environments. Rare objects will be identified as outliers rather than mysterious anomalies. The career-defining aspect for current graduate students and postdocs deserves recognition. 3 Atlas represents a generational experience, one that will influence research directions and collaborative relationships for decades to come. The scientists who cut their teeth on interstellar visitor observations will carry that expertise into future leadership positions throughout the astronomical community. These researchers will design the next generation of survey instruments. They will develop improved analysis techniques, and they will train subsequent generations of scientists. The intellectual infrastructure built around 3 Atlas will compound over time as knowledge and expertise accumulate. The myth versus memory preservation challenge highlights the importance of maintaining accurate historical records alongside cultural interpretation. Future historians studying early 21st century astronomy will need to distinguish between what scientists actually discovered about 3 Atlas and what popular culture imagined about it. This documentary and similar efforts to clearly separate peer-reviewed findings from speculative interpretations serve as historical documents for future scholars. They preserve not just the scientific results, but the process by which those results were obtained, and the cultural context in which they were interpreted. The international collaboration templates established for 3 Atlas create precedents for future multi-facility campaigns. Data sharing agreements, observing time allocation procedures, and coordination protocols tested on this object provide proven frameworks for responding to future discoveries. These institutional innovations may prove to be more valuable than the specific scientific results from 3 Atlas. An effective collaboration mechanism enables better science on all targets, not just interstellar visitors. The visual legacy encompasses both scientific imagery and artistic interpretation. The first Atlas detection images, Hubble's teardrop-shaped coma photographs, and the JWST's molecular emission spectra will become iconic representations of early interstellar visitor science. These images will appear in textbooks, museum displays, and popular science presentations for decades to come. They document not just 3 Atlas itself, but the state of astronomical technology and technique in the mid-2020s. The closing montage of discovery moments tells a story of human capability, a capability expanding to meet a cosmic opportunity. From ground-based detection, through space telescope characterization, to spacecraft coordination, the 3 Atlas campaign demonstrates international cooperation at its finest. The Starfield Fade connects this specific visitor to the broader galactic context in which such encounters occur. 3 Atlas represents just one example of the material exchange that occurs constantly between stellar systems. Exchange throughout the galaxy. Its visit reminds us that planetary formation is a galaxy-wide process, not a local phenomenon unique to our solar system. The post-credits guidance for tracking future developments serves practical purposes for interested viewers. The NASA's 3 Atlas webpage will continue updating orbital predictions and scientific results for months or years to come. The ESA maintains similar resources for space telescope observations and mission updates. Reputable science news outlets provide summaries of peer-reviewed results as they appear in astronomical journals. These sources distinguish between preliminary findings and established conclusions, helping general audiences to follow the gradual development of a scientific consensus. The institutional framework for studying interstellar visitors continues evolving based on the lessons learned from 3 Atlas. The survey capabilities improve, the alert systems become more efficient, and the coordination mechanisms become more sophisticated. Each visitor teaches us how to study the next one better. Perhaps most importantly, 3 Atlas normalizes the concept of our solar system as part of a larger galactic community. Material moves between star systems. Chemical signatures from other stellar environments occasionally visit our instrument. We live in a dynamic galaxy where the planetary formation process can be studied through samples delivered directly to our scientific facilities. This perspective shift from cosmic isolation to galactic citizenship represents the deepest cultural impact of interstellar visitor science. We are learning to think of ourselves not as residents of a unique and isolated planetary system, but as participants in the galaxy-wide processes of stellar and planetary evolution. The traveler from another star has delivered its message. It has shared its chemical secrets, and it has demonstrated the interconnectedness of planetary formation across vast scales of space and time. The conversation will continue long after 3 Atlas has returned to interstellar darkness, carried forward by the data it leaves behind and the expanded perspective it brings to our understanding of our cosmic neighborhood. We met a messenger from deep time and distant space. We learned what it had to teach, and we prepared ourselves to learn even more from the next visitors who will surely follow in its wake, carrying their own ancient secrets across the vast darkness between the stars.